This is section 17.5, Divergence and Curl. We just finished Green's theorem, which had two forms, and those two forms, one of the forms had the curl in 2 dimensions, and one of those forms had the divergence in 2 dimensions. We're now going to get divergence and curl in 3 dimensions. Divergence and curl work especially well in 3 dimensions, and it makes 3 dimensions particularly special. Yeah, you'll see when we get there. But the goal here is to compute the divergence and curl and then use the curl for something. The end goal after all of these, after the whole chapter is over, is to use the divergence and curl to extend Green's theorem out of 2 dimensions and into 3 dimensions. Those theorems, when we get them into 3 dimensions, will be called the divergence theorem and Stokes' theorem, and those are the big final things. Once we finish the divergence and curl section, you'll also be able to finally understand what this exact sequence is that I've referred to on and off throughout the class. Yeah, but I think that'll be in a separate video. So let's get started on the divergence, and then we'll look at the curl in 3 dimensions after that. So first, we have this notation for the gradient of f, del f. And the first idea we have is like, what if we just thought of this symbol as like a mathematical object that we could write down in vector form? So this is our idea, is that I know what the gradient of f is. First of all, what kind of object is f? I guess f is a function where it takes input of a point in space. So I'll put an arrow here. It takes an input of a point in space and it outputs a number. And the gradient of such a function is you take the x partial derivative and put it in the x slot. You take the y partial derivative and put it in the y slot, and the z partial derivative and put it in the z slot. Now, if you look at this and you say like, well, what is this symbol? What does this del symbol stand for? It looks like I could like factor out the f here. This barely makes sense, but it looks like it. It looks like I could factor out f. And then what we decide to say is we decide to say that literally what I mean by this triangle, upside down triangle, if I write the upside down triangle by itself, then I mean this vector that's full of operators. This, I didn't divide both sides by f. This is more like we had the gradient defined first, and then we realized that it might be nice to have shorthand for this like vector of operators. And so we say if there's ever an upside down triangle in a weird place, we think of it as like the gradient operator, which looks like this. Okay, so if you take a vector field, let's say you have f, which is made up of 3 functions like this. Do you have like your idea of a vector field in your head? A vector field in 3 dimensions would be like at each point in space, there's an arrow that tells you like how the wind is blowing at that point. That means the input would be a point in space and the output would be a vector. And so like if you plugged in x equals 1, y equals 1, z equals 1, you'd plug those into a function in the first slot, a function in the second slot, and a function in the third slot. So this is a vector field. These notes are incorrect here. This should say the divergence. Because how could we make this, this del operator interact with this vector field? I can't like multiply them. They're both vectors. So like I have this partial x, partial y, partial z, and I've got f, g, h. And the question is like, how can I make them interact? The answer is there's 2 ways to multiply vectors together. You have the dot product and the cross product. And if you do the dot product of this operator vector with this vector field, this is del dot f, then that's one way you could do it. That's one way you could have this del operator interact with this vector field. So you would, to do the dot product, you multiply the x's, you multiply the y's, and you multiply the z's. And you add them together when you're doing the dot product. And this is the divergence of the vector field. So this kind of like strange idea to try to solve for del, to like figure out how we could write the del operator as a vector, it ends up giving us a really neat way to write the divergence. The divergence is this del operator dotted with the vector field. Okay, so what is the divergence of a 3D vector field? The divergence is defined as, divergence of f is defined as partial f partial x plus partial g partial y plus partial h partial z, and that happens to equal del dot f. If this del dot f comes out to 0, it has a name. A vector field that has no divergence means that there's no like spring of wind like exploding out from anywhere. That means that it's source free. Nice. Let's do some examples. The divergence is really not hard to calculate. You do the x partial derivative of the x slot, the y partial derivative of the y slot, and the z partial derivative of the z slot, and you add them together. So the divergence of this vector field is 3. Notice that the divergence is not a vector. The divergence is the result of a dot product, so it comes out to a scalar. Let's try this one. The divergence of f, which is del dot f, is the x partial derivative of the x slot, the y partial derivative of the y slot, and the z partial derivative of the z slot. Okay, this vector field is source free. For this one, the divergence of the vector field, del dot f, x partial of the x slot, y partial of the y slot, and z partial of the z slot. If the functions are more complicated, of course the divergence is harder to calculate, but I mean, overall, it's just taking 3 partial derivatives and adding them together. The reason the divergence gets difficult is because you have to keep it separate from the curl. Like you have to know the difference between them. Yeah, so this one's the divergence. Okay, so let's look at a picture and try to see if we can like understand what the divergence does in a picture. So here's a point P and a point Q. And the question asks, hey, does the graph suggest that the divergence is positive or negative at P and Q? So here we're looking back at 2 dimensions. I don't have a function. I have a vector field in 2 dimensions, which unfortunately I don't have an option for up there. But each point in the plane has a vector associated with it. So this vector field made by red arrows would be like f, and it would be something like fg, where you'd have a function in each slot. The input would be points in the plane, and the output would be vectors. So capital F of P is like a little vector pointing this way, and capital F of Q is like a little vector pointing this way. The question is, does the what does the divergence look like on the picture? So here I've got at P, what you ask yourself is like, what is partial F partial X? So we'll do part A. At P, partial F partial X. This is how much the arrows are, it's how much the vectors are changing the amount that they go side to side based on when you move horizontally. This is how much the arrows point side to side, and this says move horizontally. So to the left of P, they're going kind of like a little bit to the left. And as we move over to the right, they are going less to the left. As I go along here, it goes from F being very negative, because the arrows are pointing left, to F being less and less negative. So partial F partial X is positive. F is increasing as X increases. Then I want to look at how G is changing when I go in the Y direction. So down here, the arrows are mostly flat, and G tells you how much the vector is pointing up. So as I move up, are the vectors pointing more and more up? And the answer is yes. They're like turning upward. So this one is also positive. The divergence of the vector field is just these two things added together. So I think that at P, the divergence of F is positive. Now let's look at Q. F is how much the vectors point side to side, like how much they point to the right. And we're going to move in the X direction. So they were pointing a lot to the left, and as I move to the right, they're pointing less and less to the left. So this is a positive derivative. When I move upward, the vectors were pointing up, but as I move up, the vectors stop pointing up as much. That's the G partial derivative with respect to Y being negative. So I suspect that near Q, the divergence is closer to 0. So that's what the divergence looks like. It's like if you're moving in the X direction, how are the vectors X components changing? And if you're moving in the Y direction, how much are the vectors Y components changing? Add those together. That's the divergence. Compute the divergence. I don't have a formula for the vector field. Let me see if I have a formula for the vector field in my notes. I do. Okay. So it would have to tell you a formula. You can't just get this vector field, the formula for it, by looking at the picture. So the vector field's formula is actually x comma y squared. So let's look at part B, compute the divergence. Well, the divergence of F is the x partial derivative of the x component, the y partial derivative of the y component, and you add them together. So the divergence is 1 plus 2y. Now, what does that mean? Well, it means that the divergence is a scalar, and it tells you how much there's like a source of force at the point. You plug in a point, and it gives you a number that's like how much source there is at that point. I guess since we have a formula now, we can actually check to see if I was right. So at P, -1 was x and y was 1, so the divergence was 3. So I got that right, that the divergence was positive. At y equals -1, the divergence is actually -1. I was right that partial f partial x was positive and partial g partial y was negative, but I didn't get it right that they were approximately 0. But this part was right, which is kind of the best you can do from just looking at arrows. So here the divergence was 3, and here the divergence is -1. Okay, part C. On what part of C? I think C is referring to this circle. So this is C. On what parts of C is the flux outward and where is it inward? Well, on this part of C out here, the vector field is pushing out of the curve. All the vectors are agreeing that let's get out of here. So this is up here in the second quadrant, the flux is out. In the first quadrant, the arrows are also going out of C. So the flux is outward. So flux out in first quadrant, second quadrant, for sure. In the third and fourth quadrants, it's a little bit less clear. It kind of looks like down here, the flux is inward. And it maybe changes around here. And down here, the flux is definitely inward also. But then it switches again to the flux being outward in these parts. So it looks like we can summarize this by saying like it around, well, it looks like the flux is inward a little bit further than that. It's hard to tell. Like here is approximately where it kind of like switches. So the flux is outward when y is sufficiently big. So when y is like more than -1/2, let's say. And the flux is inward when y is below -1/2. I'm just approximating, like about here is where the arrows start switching from going out of the circle to coming into the circle. Then the question asks, is the net outward flux positive or negative? And I would say that you've got more time spent with outward flux than inward flux. So I would guess that the net flux is outward. Okay, this seems like a bunch of random questions. Like, why did we ask all these random questions? For part A and B, the question was about divergence. And for part C and D, the question was about flux. You should already notice that we're kind of like winking because Green's theorem in the flux version had to do with the divergence of the vector field. So the flux and divergence are like connected already in 2 dimensions. So what does this have to do with each other? Well, the divergence has as its like critical point of where the divergence switches is at y equals -1/2. At y equals -1/2, the divergence is 0. So we seem to get flux out when the divergence is positive, and we get flux in when the divergence is negative. And you can just like see it on a picture of arrows, and that's kind of awesome. So let me just write a takeaway here. Flux out when the divergence of the vector field is positive. Flux in when the divergence of the vector field is negative. Seems to be what's going on. Okay, so that's divergence. We won't actually get to write down the bigger, like, the like finale theorems of the class until later. We're just trying to get divergence and curl down so that we can actually do those. Yeah. So let's do a little bit of curl. So we defined what the curl was. The curl is this weird object that's in 2 dimensions. The curl is this thing that's in the circulation form of Green's theorem. And it just happened to be the correct thing to use to get the circulation, like the work done by a vector field around a closed loop. Well, in 3 dimensions, what we do is we say like, well, we tried doing the dot product of this weird del with a vector field. So I don't know, let's try the cross product. So remember, del is now this vector that's full of operators. F is a vector field, so it's got like some functions in all 3 slots. Like this might be xy plus 2, and this might be yz minus 3, and this could be x. You can cross 2 vectors as long as they're both 3-dimensional. So curl of f is the cross product of these 2 objects. So I'm going to have I, j, k along the top, del in the 2nd row, and f in the 3rd row. And we are really stretching the idea of a cross product here, because the things in here are like vector, 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 operator, 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 function, function, function. And we're like, yeah, whatever, just fine. Just do it. So it's the determinant of this matrix. I'll do the determinant by copying down the first two columns. And then let's combine them together and see what we get. So the forward ways come out positive. So this is partial h, partial y in the I direction. Partial f, partial z in the j direction. And partial g, partial x in the k direction. And then when we go backwards, we'll get partial f, partial y in the k direction. Partial g, partial z in the I slot. And partial h, partial x in the j slot. And these are all minus. What can we notice? We can notice that partial g, partial x minus partial f, partial y is right here. So the curl in 2 dimensions we defined to be kind of like this random looking mix of partial derivatives. It shows up naturally in 3 dimensions when you do this weird operator crossed with a vector field. You get this thing shows up. But the curl of a vector field, notice that the end result of the curl is a vector. It has an I component, a j component, and a k component. So you start with a vector field, you take its curl, and you get a new vector field. It's got hy minus gz, fz minus hx, and gx minus fy. And it's 3 slots. This is called curl of f. So we define curl f to be this cross product. The curl, remember in 2 dimensions, the curl represented like the swirliness of the wind, where like if you walk around in a circle and the wind helps you, that means you walked around a little tiny tornado. It means like the inside must have been swirling a little bit. The curl in 3 dimensions still kind of measures the same thing. It measures like the swirliness, but it measures the swirliness in 3 dimensions. So it contains 2 pieces of information. It's a vector. It contains the magnitude, which is how much swirliness there is, and it contains a direction, which is like how is it swirling. So like you could have swirling that was like this, and then the curl would point this way, because the curl's a vector. Or you could be swirling like this way, and then the curl would point straight up. Or you could be swirling, basically like, because there's so many more types of spinning in 3 dimensions, the curl isn't a number in 3 dimensions. The curl is a vector. It gives you both an amount of rotation and an axis of rotation. So if you have no curl, because the curl is measuring like the swirliness or the spinniness, we say if there's no curl, then the vector field has no rotation. It's irrotational. Neat. Okay, so that's divergence and curl. Divergence is del.f. It measures how much source there is, and that has something to do with flux. Curl is del cross f. It measures how much spinning there is, and that's going to have something to do with circulation. I don't know if I'm going to be able to use this picture, really. This is a picture that's showing the different ways of like that you could spin in 3 dimensions. So, yeah, like if the vector causes things to spin this way, if the vector field causes things to spin like this, then you'd get the curl would be like a multiple of I. It would be in the x direction. If things were spinning this way, then you'd get the curl would be a multiple of j. And if things are just spinning, like if things are spinning in the xy plane, they're just like, I don't know, it's like a vertical spin like this, then the only component you would have would be the k component. You'd have the component from the two-dimensional curl. Yeah, we'll just let that picture go for now. So let's actually find some curl. Here's a vector field. When you're finding the curl, you're asking, like, is there any rotation? Like, is there any spinning of the vector field at each point? So let's see. Curl F is del cross F, which is ijk, partial x, partial y, partial z, and then the vector field. You can find the determinant however you like. I like copying the first two columns. And doing the forwards ones and the backwards ones. So the forwards one, we get partial y of 5xz. That's 0. Then I get partial z of minus 4x squared, also 0. Then I get partial x of xyz squared. That actually has something. The partial x of xyz squared is yz squared. And this was attached to k. Then we go backwards. Partial y of minus 4x squared. That's 0. Technically it's subtracted. Partial z of xyz squared. It seems like this xyz squared is what's causing the spinning. This is 2xyz, and it was in the I slot. And then partial x of 5xz. That's 5z. Add it all up, and you get that curl F. Notice that we're taking the curl of a vector field, and we're ending up with a new vector field. Curl F is minus 2xyz, minus 5z, yz squared. What does this do? It tells you at any point what the rotation is like, how extreme the rotation is, and what the axis of rotation is. So let's just plug in a number. Not a number, a point. So let's pick a point and just see what the vector field does. I don't know. Let's do like 0, 1, 0. So at every point in space, there's an arrow. That's what F is doing. F is like, there's some wind. And if you pick a point, let's back up. F is, at every point in space, there's some wind. Curl F is, at every point in space, that wind causes some spinning. So if you pick a point, like let's pick 0, 1, 0, a point here on the y-axis, you could find how the wind is blowing by plugging it into F. And I'd get 0, 0, 0. So the wind is calm here. But if I take any step away from 0, 1, 0, there would be some wind. So I'll notice that around me, the wind might be swirling a little bit. The curl tells me how the wind is swirling. So even though the wind is calm, I'm like right in the middle of a little like spinning zone. And when I plug in 0, 1, did I pick a terrible point? Yeah, it looks like I did. Because this one's 0, 0, 0 also. Okay, let's let z be 1 instead. So that was at this point. At this point, the wind is calm and there's no spinning. Let's pick 0, 0, 1. When I plug in 0, 0, 1, I still get no wind. But curl F at 0, 0, 1 is 0, minus 5, 0. So curl F is pointing in the negative y direction, which means that even though the wind, so at 0, 1, 0, the wind was calm and there's no spinning. At 0, 0, 1, the wind is calm, but if I take a little step, I'll notice that I'm being like twisted in some direction. And the twist is around this axis. So it's not like the wind is blowing that way. It's like that's the axis where everything is like a little vortex around that axis. And that's what curl F tells you. So F tells you there's wind at every point. Curl F tells you how that wind causes rotation at each point. Okay, that's curl and divergence. Let's see how they interact and how they interact with other stuff. The main thing is that because they are dot products and cross products, they behave the same way as dot products and cross products. So like if you're doing del dot is divergence. So if you have two vector fields and you add them together, well, the dot product distributes. So this means if you take the divergence of two vector fields and add them together, you can also just add the vector fields together and take the divergence. And then the dot product behaves nicely with scalars. So if you just like triple the wind, that triples the divergence. I shouldn't put a dot here next to the C. Same properties work for cross products. So if you take the curl of two vector fields added together, you could split them up actually into two pieces, do the curls of those separately, and then add the curls together. And similarly, if you scale up a vector, like if you just double all the wind, then you get double the spinning. Okay. Let's just see what happens if F is conservative. So the end of this section is like, how do divergence and curl interact with each other and with the other stuff in the class? So if F is conservative, that means that the vector field came from a gradient. Okay, now this del is getting used 3 different ways in these on the screen right now. Here's divergence, here's curl, and here's the gradient. But you can tell from context, if the del is being treated like a vector and it's being dotted or crossed with something else, then you know that it's divergence or curl. It would have to be dotted or crossed with a vector. So these objects in here are vector fields, where this thing is a function as opposed to a vector field. So the function would be like it takes input of a point in the plane or a point in space, just like the vector fields do, but its output is a number. So here this is the gradient of a function. This function is a function from points in space that gives you real numbers. So in particular, F is this vector field. It's the gradient of a function. So it's a vector field that's just made of the partial derivatives of some function. Okay, well, if F is conservative, then the curl of F does something strange. I'm just going to calculate the curl of F. It's going to be del cross F. So we get the del across the second row and F in the third row. Copy down the first 2 columns. Let's get this determinant. So I'm going to have the y partial of phi z. That looks like this. Phi z, but then take the y partial in the I slot. Phi x, but take the z partial. You shouldn't notice anything interesting going on yet, but I promise something really, really weird happens. Phi y, but take the x partial in the k slot. And then when we go backwards, I get phi x, but take the y partial in the k slot. Phi y, but take the z partial in the I slot. And phi z, but take the x partial in the j slot. What happened here? Well, I got phi zy minus phi yz. Those cancel if the function is sufficiently like differentiable. Phi xz minus phi zx, those are the same too. Yx and xy, those are the same. So if your vector field is conservative, its curl is 0. Let's try to remember like what conservative vector fields were. A conservative vector field was one where it has a potential function, and the force that it does on something is independent of the path you take. So like for a conservative vector field, if you go around in a loop, the vector field net effect on you is 0. The like prototypical conservative vector field is gravity. We say like, if I take this ball and it's at this height, and then I like move it around, but I do it in a loop, gravity helped me on part of that and hurt me on part of that, but it's a conservative vector field, so the net effect of gravity there was 0. So a conservative vector field is one where going around loops has net effect 0. In those situations, the curl of f is 0. And that makes sense, because the curl of f tells you how much like spinning there is in the vector field. If gravity had like a little space here right in front of me, where gravity like just a little bit was like spinning this way, then I could gain energy. Like gravity would help me make this loop. So the curl of a vector field and a vector field being conservative are linked in this way. If the vector field's conservative, where it never helps you spin, then the vector field doesn't have any rotation. The curl is 0. And that's this theorem. Suppose f is a conservative vector field, so it's the gradient of a function, and the function has continuous second partials, which is what we needed to make this argument. Then curl f is 0. So in particular, if you take the curl of the gradient of anything, then you get 0. Yep. Cool. Yeah, you really need to watch the exact sequence video to really piece this all together. But this is the other piece that will go into the exact sequence video. So what's the divergence of the curl is the next question. Well, wait a minute. What? Okay, divergence is you take del and you dot it with something. Curl is you take del and you cross it with something. What do you mean, what's the divergence of the curl? Well, you choose a vector field f. We'll have to give its components names so we can work with them. Then let's find the divergence of the curl of f. Okay, well, I can find curl f first. That's this cross product. And I think we did this one before. Like we wrote it down in general on a previous page. It's this thing. hy minus gz this one should be like fz minus gx, and this one should be gx minus fy, I think. fz minus gx. Oh, fz minus hx, my mistake. In the x component, you've got like all of the way that to remember this, if you ever need to remember the curl and you can't like compute it manually, is like there's no x stuff in the x slot. So f is missing and x is missing. And then there's no y stuff in the y slot. The g is missing and the y is missing. And there's no z stuff in the z slot. No h, no z. Okay, so this is curl F. Let's find divergence of curl of F. So we're going to do del dot this thing. So we're going to dot partial x, partial y, partial z with this curl. And just like on the previous page, you should believe that no one would ask you to do this unless something good was about to happen. So we take partial x of the x slot. So I get hyx minus gzx. Then I take partial y of the y slot. So I have fzy minus hxy. And then partial z of the z slot. gxz minus fyz. I've got all these second partial derivatives again. And if you look at the f ones, I've got fzy minus fyz. If these second partial derivatives are continuous, then those are equal, and so they cancel. Similarly, gzx and gxz, hyx and hxy, they all cancel, and div curl f is 0. If you write it with a bunch of dels, you get del dot del cross f is 0. Yeah, so those are the properties of divergence and curl and what's going on with all that stuff. To really like piece it all together into one big fact, you need to watch the exact sequence video. The exact sequence video is not really part of Calc 3. I don't know why it's not part of Calc 3, but like it's technically not, it's not required to think that way. But if this section just felt like a mass of like weird facts, I promise that later on, if you do physics in 3 dimensions, like the divergence and the curl are going to keep coming up, and you will need some kind of nice way to organize all of these thoughts. So I really recommend you watch the exact sequence video. Anyway, that's 17.5. Your goal here was just to compute divergence and curl, and then use curl to tell if something is, if a vector field is conservative. Curl equaling 0 means the vector field is conservative. So go do some practice problems. Just don't be afraid of the huge mess. It's just dot products and cross products. And usually the problems are set up so that they work really nicely. See you for the next section.